So the topic of the day is numerical integration. And we're going to take a look at two numerical integration techniques today. One is called trapezoid method, and the other one is called Simpson's method. The closest thing you have seen to this before is Newton's method. Newton's method was a numerical technique to solve equations. You did not get an exact answer, right? When you did Newton's method, you get an approximate answer. And yet the approximation can be made really, really well if you do, if you satisfy that the error should be very small. You can then keep repeating the iterations. So this technique called trapezoid method is a numerical technique to find the integral of a function. So for instance, if we wanted to integrate something like this, the integral of e to the negative x squared, which we're going to do this today, let's say over the limit say from 0 to 2. Could we have used u substitution here? How can we use u substitution? We could say let u be equal to negative x squared, right? Then you would need to have an x dx in there, right? Do we have an x dx? No, all we have is a dx. So this question cannot be done by u substitution. Now, in Calc 2, you guys are going to learn many other techniques of integration. But let me just give you the secret that even after all those techniques, this function just does not have an antiderivative. It just cannot be done with any technique. It's been proven not to have an antiderivative, a clean, simple antiderivative. So what do you do in a situation like this? Engineers may still need to integrate this. For example, when you deal with the probability distribution, the bell-shaped curve, somehow that function has an e to the negative x squared in itself. And they still need to find that integral to find the area under that curve. So the answer comes from numerical methods. It may not have an antiderivative, but we can still determine this integral with relatively good accuracy. But our answer may not be, let's say, the square root of 2. That may be the exact answer, but we can get like 1.4142. We can get a pretty close approximation to the actual answer with the techniques that we're about to discuss. So this is actually also how your calculator works. When you press the FNINT key of your calculator, the function integration key, chances are it's using some sort of a numerical technique of integration. It could be trapezoid method or probably something a little bit more advanced, something that converges even faster. So to understand trapezoid method, and that's what I'm going to do in the next few minutes, I'm going to try to derive the formula for trapezoid method, and then we're going to get to the examples. To understand it, first we need to remember what the area for a trapezoid is in the first place. Okay, let's say that we have this trapezoid right here. The width is 8 units. Let's say that the height is, it has two heights. Let's say this side it's A units and this side is B units. Then the question is, how do you find the area of this trapezoid? Okay, so there's a little trick we can do here. We can look at this as a rectangle plus a triangle. The rectangle on the bottom, underneath this dotted line, and the triangle above it. Now, what is this length right here? Right, because it's supposed to be a rectangle, that's a straight line. You expect this to be A units. And what about the height of that triangle? B minus A, exactly, because the entire thing was B, so this distance up here is B minus A. Now the area of the trapezoid equals the area of the rectangle plus the area of the triangle. Now what is the area of the rectangle on that picture? A times H. And what about the area of the triangle? Triangle is base times height over 2, right? The base of this triangle is H units. The height of this triangle is B minus A units. And you have to divide everything by 2 for the triangle, base times height over 2. Technically, we have a formula, but you can clean this up a little bit. Let's distribute the H over 2 over B minus A. So this can be written as A times H plus 1/2 BH. Who can tell me the last term here? I've already done this one. You need to do this one. And that 1/2 belongs to both terms, basically. It's like H over 2 being multiplied by B, H over 2 being multiplied by negative A now. So what will this next? So basically we're expanding this quantity, h over 2 times b minus a. I wrote down the first term for you, right? 1/2 h times b, right? So minus 1/2 AH is remaining, 1/2 AH. Okay. And can you simplify this a little bit? Because here we have AH, right? And then at the end, minus 1/2 times AH. So what is remaining then? If you take half of that quantity away, you're going to be left with 1/2 A times H plus 1/2 B times H. Now, could I factor out anything? What should I factor out? 1/2 H, take out 1/2 H. What is left inside the parentheses? A plus B, correct? Now, if you look at your handout, I believe on the very top of the handout, I gave you this formula. I didn't derive it on that handout, but it says 1/2 H times A plus B. That is the area of a trapezoid, so we just saw why that is the case. I think I saw somebody's hand go up. Was there a question? Yes.
The AH disappeared because you combined it with the 1/2.
Right. Basically, I have one of, think of it like x minus 1/2 x. So I was left with 1/2 x, basically, exactly. So in words, you can try to remember the area of a trapezoid as, like one other way to write the same thing would be like this, h times a plus b over 2. So one way to remember it is as follows. You could say, find the average heights, because a plus b over 2 is like the average of these two numbers, right? So find the average height of the trapezoid and multiply it by the width, which is h. So the area of a trapezoid is the width times the average of the parallel sides, basically. In other words, the average height, the way we have this trapezoid standing, basically. Okay, so we're going to use this formula to get the trapezoid method for integration. So let's take a look at now the same question we've been having all along in this last chapter, which is how do we find area under a curve? And I'm assuming that we're going from a point A to a point B, so your left endpoint corresponds to A, so your x sub 0 is the same as A. So we have the partition as we've had in the past. You have n. I'm not going to say rectangles this time. Instead of rectangles, what we have here are trapezoids. Because a rectangle would be something like this. Okay. This would be your rectangle if you join them like this. But let's say your curve is going like that. So what you do is you get the right height, you get the left height, and instead of joining them with a straight line, what we're going to do is we're going to join them with a slanted top. A slanted top basically makes it a trapezoid. So what we're going to do is we're going to, instead of covering that area under the blue curve with rectangles, we're going to cover them with trapezoids. And what is a trapezoid? Basically, it's a rectangle with a slanted top. Okay, so instead of joining it with a horizontal top, we're joining it with a slanted top. Now, which one do you think will approximate it better, the area under a curve? A rectangle or a trapezoid? A trapezoid, because it minimizes those gaps. Like, look over here, the picture I just showed you. If you took the right endpoint and did a rectangle, this is the rectangle you would get. But if you take the slanted top, so you get the right height, you get the left height, and you get the slanted top between them, that doesn't have that extra gap there that the blue rectangle had, right? So trapezoids basically estimate the area under a curve more rapidly. Like, you may need 100 rectangles, whereas you might need only 20 trapezoids to get the same estimation. And in just a little bit, we're going to look at one more technique. On the bottom of your page, it says the Simpson's rule. And the Simpson's rule doesn't use rectangles, it doesn't use trapezoids, but it uses parabolic rooftops. So it actually has a rectangle, and on the top it uses a piece of a quadratic function, a piece of a curve, which is going to work even better. It's going to estimate the area even faster than a trapezoid or a rectangle. Okay, so we're in search for this formula, and once we get the formula, it becomes very mechanical. Our calculator is great, just like it was with Newton's method. It's going to work very well, very efficiently. We're just searching for the formula. Once we have the formula, it's going to be pretty straightforward. So first step is to say that the integral of this function equals the sum of all the areas, a sub 1 plus a sub 2 all the way to a sub n. That's what I have over here. The sum of the all n trapezoids. Okay, the first thing I will ask is, what is the area of the first trapezoid? And we just learned a formula for it, right? The area of a trapezoid is the width times the average of the two parallel heights. So who can tell me? And here, normally we use delta x, right, to represent this thickness over here. Usually we use delta x. For this section, to make notation a little bit easier, I might, instead of using delta x, I might just use the letter h. It represents the same thing. If you like, if you prefer delta x, stick with delta x, that's fine. So can you tell me what the area of the first trapezoid will be here? Okay, the first height, since you plug this number into the function to get it, the first height is f of x sub 0. And the second height is f of x sub 1. So basically, we're trying to write the area of that one little trapezoid. So what will that area be? The width is delta x or h, right? Okay, it's in your handout once again. Let's remember, what was the area of a trapezoid? Area of a trapezoid equals 1/2 times h times a plus b. A plus b are the two parallel heights, right? So for this particular question, it's going to be 1/2 times, you could say h or you could say delta x. It's up to you. Same thing, okay? Times, okay, now I want a plus b. What is my a plus b for this question? Okay, let me see if everybody agrees. F of x sub 0 plus f of x sub 1. Would everybody agree with that? Okay, the left height and the right height. Okay, now tell me the area for the second trapezoid, and you're going to see a generalization from here. The second one will have 1/2 times h times, the left border is f of x sub 1, and the right border is f of x sub 2. And let's just say dot, dot, dot. Let's write the last one now. 1/2 times h times. Can you write the last one? Exactly. The left border is f of x sub n minus 1, and the right border will be f of x sub n. So we have everything covered there. Okay, the only thing is now I need to simplify this before I can give you the final formula. Let's see, I don't need that square bracket since I did not open one. I should not be closing one. Okay. So we just need to simplify this a little bit. Let's take a look at the following situation. So f of x sub 1 is used here, and it's also used here. As a matter of fact, I think I'm going to do something. I'm going to, okay, please ignore all of this right now. I'm going to, see. I'm going to delete all that. Okay. So let's simplify that a little bit more to see where the formula comes from. Okay, so take out a 1/2 h out of everything. Take out a 1/2 h. So then you would have, from the first quantity, you would have this, which is f of x sub 0 plus f of x sub 1. Okay, what would you have from the second quantity? If you took 1/2 h out of this one, what would you be left with? Exactly. And let's just put dot, dot, dot. And the last two are going to be these. Okay. Now, do you see that you're going to have two of certain quantities, like f of x sub 1, you're going to have two of them. Why? Because one, it was the right endpoint of the first trapezoid, and then it was the left endpoint of the second trapezoid, right? F of x sub 1 was the right endpoint of this trapezoid, but it's also the left endpoint of the second trapezoid. Same thing with this. F of x sub 2 is the right side of a sub 2, and it's also the left side of a sub 3. So a lot of the things are going to be simplified. So for example, but how many f of x sub zeros do we have, do you think? One or two of those. That's the left-hand border of the first trapezoid. That one is not being shared by any other trapezoid, right? So there's only one f of x sub 0. So there's going to be only one f of x sub 0. How many f of x sub 1s? 2. How many f of x sub 2s? 2, because everything is being shared until you reach the last few steps, right? How about f of x sub n minus 1? How many of those are we going to have? 2, because again, this is being shared as well. But the last one, which is f of x sub n, is going to be just 1. So this, ladies and gentlemen, is the formula that we've been looking for. This is the trapezoid formula. That we're going to be using to find the integral of a function numerically, which is going to be an approximation. If you know what the function is that you're integrating, notice there's no differentiation here, there's no integration here. This is arithmetic. You're going to add up a bunch of points. You're going to multiply them with 1 or 2, depending on what the point is. And you're going to add them up. It's just simple arithmetic. We're going to find the total area. Now, guess how you could make something a better approximation? Like, for example, if you had 10 trapezoids versus 20. Clearly, 20 trapezoids is going to approximate it better, right? Just like rectangles. The more the rectangles, in this case, the more the trapezoids, the better the approximation. So usually, for most problems I'm going to assign you, I'm going to assume n equals 8, okay, so that it's reasonable, it's easy to calculate. But in reality, if you let a computer do this calculation, you could just as easily make 50 trapezoids or a large number, so you'll get a very accurate answer as your integral. So I'm guessing your calculators were programmed to have a large number of trapezoids or rectangles, so it'll come up with a very good estimation with that FNINT key that we're using. Again, that must be some sort of an approximation that the calculator is using. Okay, finally, there is one more formula. This other formula is called Simpson's method. And I'll just give you the general idea there for the Simpson's method, the general idea. Okay, you already know a little bit about this. Instead of having trapezoids, what is this going to have? So let's say that you have instead of joining with straight lines, it's going to join with basically parabolic tubs. And the way this is done, usually they take two rectangles that are next to each other, and they join the rooftops of them with a single parabolic equation. And this formula is a little bit harder to understand. So I'm just going to give you a very general idea. I'm not going to prove this entire thing, so that I can also give you the formula quickly. Here's a general idea. If distance is h, and again, if this is your point x sub 0, right here, the first one is x sub 0. This next point is x sub 1. And the next point here is x sub 2. And if this red curve is your f of x, there is a theorem that states the following. It says, the area under a parabolic arc, that the area under this let me make it simple. Just say integral. The integral from x sub 0 to x sub 2 of the function, basically the area under this parabolic region, which is, it has a rooftop of a parabola and rectangles on the side. It says that this is equal to 1/3 times h times f of x sub 0 plus 4 times f of x sub 1 plus 1 times f of x sub 2. No, we're going to get there. We're going to get to the formula you have on your sheets, but this one says that if you have a situation like this, where you have basically trying to find the area under a parabolic segment, it says it's 1/3 times h times f of x sub 0 plus 4 times the middle height plus 1 times the last height. Now, if you were to apply this for an entire region, and I must say that with Simpson's method, you always use, your partitions have to be even because they always use 2 plus 2 plus 2 rectangles with parabolic tops. You can never have an odd number of partitions because of this theorem. This theorem only works when you have two right next to each other. And the reason that works is because basically you have 3 points. You have this point, and that point. If you have 3 points on the Cartesian coordinate system, there's only one parabola that will go through it. You can uniquely determine what that parabola is. Like if there are 2 points on the Cartesian coordinate system, there's only one line that will go through them, right? For 3 points, there's only one quadratic function. So this idea uses, what that equation is. So I'm just giving it to you as a theorem. It turns out to be the area under that turns out to be this. But you need 3 points. Therefore, you need 2 of those rectangles to be able to make this true. This is the reason why with Simpson's method, you're going to need even number of partition points. Okay, finally, if you were to do the same thing we did a moment ago, which ones are going to be shared? This is going to be shared side, and this is going to be shared side, right? This one is not going to be shared, right? If you keep doing like another one like that. As a matter of fact, I'm sorry, this first one is never shared, but this is going to be shared, this is going to be shared, etc. So I'm going to give you the formula now and see if you can kind of visualize how this comes about. The formula turns out to be the following. So the formula from the same area as we had a moment ago, same area. With the Simpson's method, here is what the formula turns out to be. With the Simpson's method, so what I'm about to write is the Simpson's formula for the integral from a to b of the same region we were discussing earlier. So integral from a to b of f of x dx. Okay, so instead of 1/2 times h, now you have 1/3 times h. That's because of the formula we have just seen, right? That formula has 1/3. Now, the very first point is going to be 1 times f of x sub 0, based on that formula we just saw, 1 times f of x sub 0. The next point is going to be, any guesses? 4 times f of x sub 1, because this point is not being shared. This point here, because look at these as groups of like together, groups of 2 rectangles next to each other, then the next 2, then the next 2. So this one is not being shared. So that one stays as 4 times f of x sub 1. But this one will be shared. So what will be the coefficient of that one? 2 times f of x sub 2. Because that one is going to be shared with the next rectangle. So you're going to have one coming from the right side of the first rectangle and one coming from the left side of the second rectangle. So that will be 2 times f of x sub 2. Why is the middle one 4? Yes, that came from this formula. This formula right here said, if you have basically, you have to look at them as pairs, okay? 2 next to each other. This is the way you can look at them with the Simpson's method. The formula says if you're trying to find the area under this parabolic top, basically the area of this plus that rectangle, the formula says it's going to be 1 times this height. So first of all, you have this coefficient, then 1 times f of x sub 0, which is this height, plus 4 times this height, plus 1 times this height, correct? That's what this formula is telling us. 4 is part of the formula, right, for the parabolic tops, yes. Now, I could, next time, if you're interested, I can give you a proof of where that formula comes from. It's like a page long. If anybody's interested, let me know. I'll give you a proof. Because this one, I apologize, I did not derive this formula because it's a long formula. Okay, so I just gave it as a theorem, and now we're using the result of the theorem. But if anybody's interested, I can make you a copy of this, okay? So the formula said this is 1 times this, 4 times that, and 1 times this. But when you look at the next group of 2 two rectangles right next to them. Now this, what is it going to be, the area under this? Similarly, it's going to be 1 times this height, 4 times this height, and 1 times this height. And because this border is being shared with this group and with the other group, that's why you end up with a 2. Okay, so this is why we're going to have a 2 here. Where's my formula I was about to derive? Okay, so we have 1, 4, 2. And then the middle one is not shared, and from the formula that was a 4, had a 4 coefficient, 4 times f of x sub 3. And then the next one is going to be shared, so it's going to be 2 times f of x sub 4. Basically, the pattern turns out to be, and the last one is not shared at all, so it's going to be f of x sub n. So this should be in your handout, this formula. And I'm just going to simplify it for you a little bit. The coefficients are like this. If you were to look at the coefficients within the brackets, it's going to be 1, comma, 4, comma, 2. Basically, it alternates between 4s and 2s. And it ends with a 4, 1. So it starts with a 1, 4, and it ends with a 4, 1. And what are the coefficients for the trapezoid formula? Let's also summarize those. For the trapezoid, they're very simple. Okay, the coefficients are 1, comma, 2, comma, 2's all the way, right? Except for the last one, it's a 1. Okay, the trapezoid method is a lot easier to understand, but just know that Simpson's method converges faster because it has parabolic rooftops, in a sense, on the rectangles. Okay, now that we have the two formulas determined, we're ready to do some examples with them. Okay, the first example we're going to look at is going to be a simple one.